Hello, I'm Shaumik, and I'll be presenting our work Uncertainty Quantification for Ground Truth Tree Evaluation of Deep Learning Reconstructions. I have no financial interest to declare. Deep learning-based techniques have become an integral part of medical image processing research. However, the complex reasonings performed by these models make them appear black box to us, which makes it difficult for clinicians to trust these models. This also makes the in-depth evaluation paramount. The models are typically evaluated by comparing their output with the corresponding ground truth. As the models are black box in nature, evaluations on large test datasets with as many use case scenarios as possible are performed to check the model's stability, generalizability, and applicability in clinical scenarios. Nevertheless, when used in clinical practice, there is no available ground truth to compare and evaluate the predictions. One possible solution is uncertainty quantification. This research aims to evaluate super-resolution models without ground truth with the help of uncertainty quantification. For our approach, we have used ICSI T1-weighted and T2-weighted MRIs, which were trained and evaluated separately. The images from the dataset were considered as the fully sampled ground truth. They were artificially downsampled by taking the center of the K-space with 5 different undersampling factors ranging from 2 to 4 in all 3 dimensions, resulting in theoretical acceleration factors from 8 to 64. 3 deep learning super-resolution models were included in our research: the residual dense block, or RRDB, which is the generator of the ESR-GAN, then UNet and UNet MSS models. The training and inference were performed using 3D patches with a patch size of 64 cube. During training, for each epoch, 60 patches were randomly sampled from each volume. The loss was calculated using the Structural Similarity Index, or SSIM, and was minimized using the Adam optimizer with a learning rate of 0.001 for 50 epochs. An auxiliary system with uncertainty modeling was built to be applied to a trained model by adding infer dropouts inside that model during inference. In the RRDB model, the dropouts were placed at the end of each residual dense block. In case of UNet and UNet MSS models, dropouts were added after each contraction path and expansion path blocks. 5 different dropout rates ranging from 1% to 50% were used. The same dropout rate was used in all the different locations where the infer dropouts were placed. The model predictions were generated from low-resolution images using the trained model weights, but with different dropout rates. Then the final uncertainty map was calculated, which is basically the pixel-wise variance across all these generated images. Now let's have a look at the results. On the top, we can see the fully sampled image. Then we have the undersampled versions with different acceleration factors. The next row shows the output of the model. The resultant SSIM values for these images are also shown in the figure. The second last row shows the differences between the reconstructions and the ground truth, which is a typical way to evaluate super-resolution models when the ground truth is available. And the final row shows the generated uncertainty maps. From the resultant SSIMs and the different images, it can be said the performance of the models for theoretical acceleration factors 43 and 64 are not good, and they cannot be trusted for real applications, a finding which is also corroborated by the uncertainty maps. Another notable observation is that the model was uncertain about the structures containing liquids like cerebral spinal fluid and eyes. This warrants further investigation. UNet model also results in similar findings as the RRDB model, as well as the UNet MSS model. A comparison of the UNet and UNet MSS uncertainty maps tells us that introducing multi-scale supervision also reduces uncertainty of the model. Finally, the generated uncertainty maps were evaluated by computing the correlation with the L1 loss maps and also using the mean uncertainty of those models. Here it can be seen that the mean correlation of the UNet model was the highest, whereas the mean uncertainty was the lowest for the UNet MSS model. On the right-hand side, the mean variance map of the uncertainty is shown with the help of kernel density estimate plot. Now to conclude, we explored the possibility of evaluating super-resolution models using uncertainty quantification. We did an evaluation of 3 different models and 5 different acceleration factors. The results showed that these models could achieve trustworthy reconstructions up to a theoretical acceleration factor of 27. This research demonstrated the potential of using uncertainty quantification for ground truth-free evaluation of these results of super-resolution models. Thank you so much for your attention. Please feel free to contact me for any questions or feedback.